Hello. Hello and welcome to this video on multi-threading with POSIX threads using C. So we will start with the three programs. Now I can talk about theory about multi-threading and concurrency, parallelism, synchronous and all that. But the best way, in my opinion, is to show practical. So here we go. Now consider this program, okay? We have three variables: seconds, a character buffer of 128 characters, and a message of 65. Okay. Now, what we do is we have an infinite loop. We print alarm. We take the line. We read a line that is this 128 character buffer. And if the length is less than 1, we continue. That is, we skip the loop. And if it returns null, we exit saying return status is 0. Now, if the return value of a status is not null and the length of the line is greater than 1, we do a scanf, we pull out seconds and message. So what we are expecting in this line is input is one number, which will be number of seconds, space, a message. Okay. Once we have these two things, we sleep for those many seconds and then we print the message. We print the seconds also in parentheses and we print the message. Now this is a classic synchronous program. Why? Because suppose we enter 5 seconds with some message, okay? Then what will happen is this loop will suspend here at line number 21 while it will sleep. It can't do anything other than possibly respond to signals. So for example, sigkill or sigturn or sigint. So those signals it can process. But other than that, it can't do anything because it is sleeping. So let's see this in action, okay? So the name of the program is sync.c. We compile this gcc minus wall minus w errors minus std is equal to c23 minus pedantic, and we say sync.c. So now we have this read it out. We give a very small timer, few seconds, and we say wake me up, wake me up. No space, okay? This percentage does not take a space in between. And then you see we have to wait. And after 2 seconds, it says wake me up. And similarly, we can say 5 space wake me up. And after 5 seconds, it will say wake me up. It is straightforward, simple program. So it says wake me up. Now we give it EOF character, that is control D, and it bails out. Now we look at another program. This one is slightly involving. So let's see. The core is the same. We have another variable PID. Now you should be aware of some system programming for this program, but I'll try to explain as much as I can. Okay. So similarly, we read the line. If it is less than 1, we continue. Now we read if it is less than 2, then bad command. Now in the else block, the magic starts. What you are looking at here is a fork. Now fork, what it does is it clones the calling process, creating an exact copy. So whatever our program has, it will create an exact copy. Now you see it returns -1 for errors and 0 for the new process, and the process ID of the new process to the old process. So we see that if PID returned here is -1, we exit because there is an error, we can't create new process. Now if it is 0, then that means it is inside child process. Okay. The parent receives the ID of the child. So we sleep for those many seconds, and we, after sleeping, we exit the child process. Okay. So this is for child process. This block is for child process because PID here is 0. But if the PID is not 0, That means it is a parent process because fork will return a PID to the parent process as well as that to the child process. So now there are two different branches here of code execution. One branch is this, the other branch is this. Now in the parent process, what we do here is we call wait PID. Okay. So what it does is that it waits for the parent child to die. Okay. And if PID is -1, it matches any process. If PID is 0, matches the process with the same process group as the current process. So other things are uh, simple stuff. W no hang has a different meaning. Okay, let me show you the exact thing. And space wait PID. So see, no, not command. And space 2. So this is the full signature of that. So W status we passed null, and then we pass W no hang. Okay. So let's look for W no hang. So return immediately if no child has exited. Okay. So this will immediately return, and if PID is an error over here, then it exits. And we do this while PID is not equal to PID 0. Okay. So it will continue till the child exists. Okay. Now let's see this in action. Okay. So we compile like that, and we are multi-prop.c. So we do a.out, and now we give it 10 seconds, and we give some message. Now if you see here, so if we look for a.out process, a.out not found. Open top system, and we say a.out. You see there is a process a.out, and if you want, there should be another one. There should be two because I can grab and better away. Yes of www right grab a.out. So we see two processes. One is defunct, another is running. So it printed the message. So that process, there is something wrong with that. So it became defunct. So you see here, one is defunct, another is running. Now, if you see this, it is the PID of the child. This is the PID of the parent. So it might have become a zombie process. So it has become a zombie process. Okay. Now we give 5 space, wake me up. Now see, it returns immediately, and we can give it another command, and we can give another. So you see, this will all come here. So all these processes are running. Okay. The zombie processes was eventually collected by the parent process. So at this moment, 3 processes are coming, running. This is the parent process, and these are children process. So from this, you can see that while the child process is running, we can give it more commands to create more child process. So we can create as many child process as we want, provided the timer is long enough. So for example, we give 100 and we say 100, and we give it 200 and we give some message, 300 and give some message, and 300 and give another message. Now see, 4 process would be running. So 4 child process and 1 parent process. And all these are running their own separate timers. It is not one timer. As you see in the sync, there is no way to have 2 timers. You can have only 1 timer. Okay? Because as soon as you give the command, it goes into sleep mode, and the main thread is blocked now. But in this case, main process is not blocked because the child process, main process can run this again and again and again. Okay. All right. So now we have this. So we continue to the next one. It will keep running. It will take a long while to give the output. Okay. Now we do Control C, then there is no such process. All processes are cleaned up. Okay. Now we see multi-threaded example. Now we'll see a multi-threaded example here. We have an alarm tag and note the usage of pthread.h header file. We have a structural alarm tag. It takes a second integer and messages of 64 characters. Now we have function alarm thread, which takes a void argument. Now we passed this alarm to the argument, alarm tag pointer to argument, and we have status here. So the thread which we have is we detach that, okay, and give it the self threads ID. It is the ID of this particular thread only, and we detach it. Now if status is not equal to 0, then we print the status and we detach the thread. Error is a simple macro here which prints messages at standard error. Most probably you won't see this. Okay. Then we sleep for seconds in the alarm tag argument variable. However, seconds are supplied, we sleep for that. Then we print the seconds and message like earlier, and we free the alarm tag here. Alarm tag would be allocated in the main thread. So here we do the same stuff here. Okay. Now we malloc here the alarm tag which we need to pass to the thread. And if it is null, there is allocation failure and we abort it. And then we similarly read the seconds and message from the alarm and we free alarm if it is less than 2. Now here the magic happens. We create pthread create. Now if you see the, let me show you. So what does it take? Okay, it's not clear here. Okay, let me show you here. Man space 3 pthread underscore create. So it takes the first argument is a thread, which is the thread here. Okay. Now this thread holds a pthread ID. Okay. And then we have null. This null is basically attribute, which is nullable. So we have part null. Then the third argument is a function pointer, which is alarm thread, not function. This is, yeah, function pointer. Okay. And the last argument is the argument which we supply to the thread. So you can supply anything because it is void pointer. So it can take anything. We can supply anything by address. And then the thread runs. And if status is not equal to 0, then there is problem in creating alarm thread. Now once the thread is created, it will run on its own. And when it's done, it will be done. While the main thread, that is this program thread, is again, after creating the thread, it does not wait for it because the thread is detached and it will continue this again and again and again. So it will wait here for us to give the instructions. Now to compile the program, we do the same thing. This is multithread.c. Now one thing we have to do is we have to do -lp thread to compile this with POSIX threads. Otherwise it won't work. Let me show you this. Oh, it worked. Very nice. It shouldn't have worked, right? It requires LP thread. Anyway, looks like it is embedded into the library because earlier, if I remember, we used to have LP thread. The pthread is required. Let's see this. Now we see ldd.out. Okay. And what if we compile it with pthread? Okay, so looks like pthread is built in anyway. So we run this and we say we give it last time. First we give small time hello to hello. So you see immediately the thread ran and 1.hello came out, 2.hello came out. Now we give it 100 hello. So you can see that it will go on creating the threads. Okay. So like multiprocessor program, like the second program, the third one also does not wait. So now what is happening is This thread is now independent to run. When we create this, it is independent to run irrespective of what is going inside the while loop. Whether we are taking the prompt, waiting for prompt, or we are doing memory allocation, or we are printing, irrespective of that, this thread is running. It might be most probably running on another CPU. Okay. So may run on the same CPU. If it's a single core, it will most probably run, it will run on the same CPU. But if it is multi-core CPU, this may get scheduled onto another processor. So that's what is the important part. So when we talk of concurrency, that means that it is independent of the main thread. A thread is independent of main thread. Now, something I want to talk about the synchronous and asynchronous operation. So as you see, this is synchronous operation. You have to wait for sleep to complete before you can schedule another alarm. So you can have only one alarm. But in multi-process and multi-thread, at the same time, you can have n number of programs running in, or rather alarms running in. So this is possible simply because we free up main thread from the actual sleep. Okay, that is why we uh, we are able to schedule the another more than one alarm. Now here, let me explain wait PID a bit more. Okay, because I don't think I did justice with wait PID. So utility to wait, not this. So wait for process to change state. So you need to read this description to understand this. Okay. Now what we are waiting for is while PID is not equal to 0, meaning wait for any child process whose process group ID at the time of call is that of the calling process at the time of call to wait PID. Okay. So that is what we are waiting for. As soon as the child process whose process group ID is equal to the corresponding calling process, then we do not wait any longer. Okay, we are waiting for this to become 0, PID to become 0. Okay, so that is the entire thing we are doing it. The wait PID system call suspends execution of the calling thread until a child specified by the PID argument has changed state. Okay, so what do we mean by state? So you will have to read this entire documentation of wait PID to understand this. Don't worry about this. This is essentially mean that we use one process to sleep and then we go and schedule another alarm and schedule another alarm and schedule another alarm in the loop. After multi-threading, I think I will go and cover a bit of system programming so that we can cover this. Maybe I'll run a new playlist before returning to C++ thing. But the essence of the this program is that you have a parent process, you schedule an alarm, the child will take care of the alarm, then you schedule another alarm, and then you schedule another alarm. So an analogy can be drawn in this is like, I'll give you the classic example of Apache web server, which behaves more like this. It listens on port 80. A network request comes for serving an HTTP request. Apache main process takes it and passes the request or not, doesn't matter. Basically, it offloads the work to another process. Then another request comes, it offloads to another process. And it has an upper limit of how many processes it can have. So it goes on offloading to those processes. Those are called worker processes or child process. So this is more like worker process. Now you can create these process separately and have a process pool. Similarly, you can have a thread pool here. You can create the threads beforehand for a number of threads. So the essence of multi-thread programming is that if you see this program, the multi-process program, then each process will have its own address space. So obviously they will consume a lot of RAM. Plus creating a process is far heavier than creating a thread. Thread is much more lightweight compared to a process. For example, the stack address allocated, if you have 3 alarms running, then 3 plus 1 main thread, 4 times 8 MB, that is 32 MB stack space straight up this will consume. But this program is limited to 8 MB. So I don't know how many process you can threads you can create for 8 MB, but you can easily create in 8 MB. Let's say one thread can, if we say assume that if we give say 64 kilobyte to one thread, then you can create a huge number of threads, although your stack space will be slashed a lot. So reasonably, the number of threads should be equal to number of processes. So I have, I believe, 24 cores, so I can spin 24 threads as such. Since this is mostly sleeping, I can possibly create thousands of threads. But that is not the crux of the discussion. The main point is that the threads are relatively lightweight compared to process. Also, you have not no. What I was thinking was a different thing. Apologies for that. So the idea of this video is to introduce you to threads. So how do we create threads? So we have thread creation here. We thread create, and threads can be joined or detached. If you join the thread here after pthread create, then main thread will wait for it. But we don't want to wait because otherwise we will be stuck with the synchronous version. So we detach the thread here and then we keep running here. So most probably this will be, if it is compute heavy, it will definitely go on to another CPU. So with this, I will just end this video here, and I hope that you have learned something of value in this video. So thanks a lot for watching the video, and we will meet again after 4 days with another video on multi-threading, where we will discuss more of multi-threading, more constructs. And so keep learning, have a nice day, and most importantly, enjoy.